Hi, Jesse.
Hello, Alan.
How are you doing?
Good. You?
Good, good, good. So the last week I was planning to write consensus programs, but in the end I didn't get to it. I was busy fixing the foundations over in TASM lib, which is our library for TASM for Triton assembler code snippets. And what I was doing there was, making the recursive verifier more versatile than it currently is, so that I can use it in the way that I want to use it when I finally do get to write consensus programs. And so it shows one of the reasons why progress is slower than anticipated is because when you are wrapping together various threads that you could develop in parallel, but are finally coming to a close where you need to wrap them together, you discover that they don't always fit together in the way you anticipated, and you need to modify the framework with which they fit together. And yeah, that takes a little
S-
more
So
effort.
maybe remind our listeners and viewers of your mental model of the project as a whole. Like with what you're working on now, and you want to work on the consensus protocols. What are the other things that have been done that are finished, and the other things that are not finished?
Right. So I want to work on the transaction validity programs, which is a subset of consensus programs. Consensus programs is anything that could cause a network split if nodes disagree about that logic. And so they obviously need to agree about what makes a transaction valid. And there are actually a bunch of features. Once you start answering that question, you'll come up with a bunch of features. The owners of the UTXOs need to sign off on the transaction. The transaction cannot have inflation, and that's a lot more difficult to ensure if the amounts are not in the clear, which they aren't. And so there are a bunch of features, and for simplicity's sake, we've delegated all of those features or relegated all of those features to their own specific program that establishes just that one feature. And then some other program will need to wrap everything together, and that's how you get a single proof for a transaction. It's by proving the correct verification of a bunch of atomic proofs. And so, in order to write this proof combiner, I need to have a version of the recursive verifier that takes two or even more proofs. And currently, it looks like the recursive verifier can only recursively verify one proof in a given location in memory. And that's enough for benchmarks, but that's not very versatile. And I guess that static memory model could be extended in theory to multiple proofs, but it cannot be extended to an unknown number of proofs, where you need to know the hash of the program before you know the number of proofs it is going to verify. And so that kind of versatility, back when we were running benchmarks on Triton VM, we didn't know that we needed that kind of flexibility. But now we do. And so now we need to go back down into TASM lib and modify the verifier so that we can write the consensus programs in the way we like.
Okay, but not a huge deal.
It's not a huge deal, but it's frustrating because it feels like we're not making progress. I mean, we're obviously making progress, but if you'd asked me on Monday, what do you hope to accomplish this week? I would have said write one or two consensus programs, and I didn't get to do that at all.
Yeah, yeah.
Um, yeah, And then Thor went down a rabbit hole answering the question, can you authenticate Merkle authentication structures efficiently using non-determinism? And the answer is yes. He wrote an algorithm for that, and it looks like probably with the current instruction set, the naive algorithm that you would come up with without using non-determinism is more
But
efficient.
let's back up first. So Merkle trees, some people might know from that know about Bitcoin, but you need to break this down for our viewers and listeners.
Right. So a Merkle tree is a data set of items arranged in a balanced binary tree where each node is the hash of the concatenation of its two children. And the nice property about Merkle trees is that the root of the tree, which is a single hash digest, binds to all leaves. And so I can prove to you that a leaf is in fact in the tree if you have the root, simply by releasing a bunch of hashes, and these hashes are the siblings of every node as I walk from my leaf to the root. And you'll be able to walk up with me and recompute the root, and then in the end you test that the root you already had is equal to the root that you just recomputed. And that's an amazing property to have from the point of view of scalability, because now I'm not requiring you to store a whole bunch of leaves anymore. I'm requiring you to store just one digest.
Yeah.
And so we are using Merkle trees, and more generally, we're using Merkle mountain ranges in the mutator set, which is the data structure where you put UTXOs into. And so as a precondition to spending UTXOs, you need to prove that certain leaves in a Merkle mountain range, you need to prove that they have a certain shape, but you also need to provide the authentication paths. And we noticed, hang on, our paths, they tend to overlap. After a short prefix, most of the time they're the same. So what if we deduplicate our paths? Totally possible. What you end up with is an authentication structure rather than a list of authentication paths. And then the question is, a peer has broadcasted this transaction, and we are requiring that the leaves really are leaves in the Merkle mountain range that is part of the global state of the node. And so we want to verify not just that the leaves are there, but that the authentication structure is authentic. That using this particular authentication structure, we can verify those leaves, and not in the abstract that there is some authentication structure. And so we'll need to have a consensus program that verifies this. And it's not a trivial task. I mean, you can write a simple program in Python or in Rust, but then you want this program to run in as few cycles as possible on the Triton virtual machine. And in order to optimize that, we started thinking, okay, how about if you use non-determinism, which is where you get to make a guess, and this guess is, divine inspiration, because this guess is always correct. That's what it means to compute with non-determinism. And that corresponds to using secret information in Triton VM. In fact, whenever a proof is zero knowledge, that knowledge that is not being leaked, the prover obtains through non-determinism, typically. And And so we came up with an algorithm, a non-deterministic algorithm for verifying the authenticity of an authentication structure. And we implemented it in Triton Assembler. All right, most of the credit goes to Thor here, and it's expensive. And right now it seems as though just naively verifying one path after another is going to be much cheaper. But then it's going to be much cheaper because Triton VM was designed specifically to make stupid verification of Merkle authentication paths fast. And so if you're going to put the two computational tasks on the same scale to compare apples to apples, we have to introduce custom instructions into Triton VM for the second task as well. And so we had a brainstorm. Which instructions could we introduce to make this task of verifying authentication structures efficient? And we came up with two instructions that we may or may not introduce. And with those instructions, we're probably going to outperform the naive approach. And at this point, we're thinking, okay, the performance gain is rather slim. What would we be getting? We would be getting smaller transactions and um, less workload on the part of transaction initiators. But we would be getting this at the cost of a huge engineering effort, which is rewriting everything that deals with lists of authentication paths into something that deals with a single authentication structure. And so we kind of made the decision that this is not urgent enough for mainnet launch. So we decided that we're going to launch with the current architecture in regards to this specific design and this authentication structure magic. Even though it's a really nice algorithm, I mean, it continues to be a really nice algorithm, and we continue to want it. But maybe we should wait until after launching to implement it, and then we can introduce it through a hard fork, which is going to come anyway.
Okay, why is it going to come anyway?
Because there are a bunch of such features that we want to introduce, and we just cannot afford the engineering time and effort to develop prior to launch.
Okay, so the rabbit hole has been sealed back up, or
Well, it's sealed, maybe not, but it's been identified and explored, and we know how deep it goes,
okay,
and
okay,
probably one day we want to return to that rabbit hole, but it won't be a rabbit hole anymore. It'll be a guided tour in a guided spelunking tour.
okay. And so where does that put us in the grand scheme of things, especially related to mainnet launch?
So the transaction validity programs are not complete yet. Such as wrapping everything together still needs to be written because until recently the recursive verification program was incapable of verifying two programs. And by the way, now that it can verify two programs, we have another difficulty, which is that it's taking a very long time on regular hardware to perform this proof. Anyhow, that shouldn't stop us from writing the consensus programs for transactions. When it gets to blocks, there's a much less clear path forward. One option is to launch with the current architecture for blocks, which is not succinct. You do not prove the correctness of the previous block, and a full node is an archival node that stores all blocks in history just as they do in Bitcoin. And then we could introduce through hard fork 1 a succinct architecture where you are required to prove the correctness of the previous block. And I like it and I don't like it for two reasons. One reason why I like it is because it allows us to get to launch, and that allows us to get feedback from what the market wants and play on that feedback. Maybe nobody cares about succinct blockchains. Then why are we wasting engineering effort to build it? On the other hand, I'm really excited about succinct blockchains. I know at least one person cares, and it feels like I'm sacrificing a part of my soul by entertaining this option to postpone it until after launch.
But succinctness that goes hand in hand with scalability, or am I not understanding it correctly?
Succinctness goes hand in hand with scalability, yes. So we would have to drop the selling point that we are more scalable than competitors. At least until hard fork 1.
If you abandon this now, or is that
well, I don't think we're going to abandon it altogether, right? We're going to potentially postpone it until after mainnet launch.
Right. So you might not be as scalable as you had hoped for mainnet launch.
Correct. And another consideration is, maybe we launch and we're not as popular as we hope. And in that case, scalability isn't a problem to begin with.
Yeah, fair enough. So that's more of a problem at the business level or at the organization level. Yeah.
Yes.
No, that seems valid. So what? Because it sounds like you guys have mostly just been in the weeds with all the technical stuff. I know the Telegram group exists, but has there been, what else have you been doing on other fronts, or is the technology front been just the main and only front?
A main and only front. Okay. We're in the process of moving offices. We're talking to people who want to do ancillary stuff. Introduce us to these other folks who might want to help. Introduce us to exchanges who might want to list us. That kind of thing. But 95% of our attention is devoted to development.
Okay, and the blog posts, of course.
And blog posts, yeah. It's worthwhile articulating my thoughts before engaging in the design process and that before developing.
And so there was one you wrote recently. Do you want to talk about that?
Yeah. So the mechanics of mining rewards, and it ties into the what is it? The perspective going forwards after we have transaction consensus programs, because blocks are definitely more innovative, less clear. Yeah, because among other reasons, because it's not straightforward to distribute the mining reward, and that's the topic of this article. And it's not straightforward for three reasons, at least. Firstly, we have two-step mining. Secondly, there's a time-locked mining reward. And thirdly, there's dynamic block intervals. So two-step mining means that you have to prove.
This is the mechanism that you've already, that's implemented now, that you're talking about.
No, these mechanisms are proposed, projected. They're still up for debate, in fact, but these are mechanisms that certainly live in the back of my mind, and you will be able to find articulations of in the white paper.
Okay.
Um, so two-step mining is where you are required to produce a proof and solve a proof of work puzzle. Um, the second one, hang on, is time locked mining reward. The idea is that if you successfully mine a block in Neptune, half or whatever proportion is of your reward is locked up for 3 or 4 years, and the other half, the remaining part, is liquid immediately. Um, and then the third one is dynamic block intervals, which is where the protocol observes that the network conditions are good, good enough to tolerate faster block intervals. And when it makes this observation, it actually reduces the target block interval. And the reason why these things make the distribution of mining rewards difficult is because, well, in the case of two-step mining, you don't want to give a consistent systematic advantage to miners with faster hardware. You want the mining power to be distributed in accordance with cheap electricity and not with fast hardware. And so
Why?
why do you want the distribution of mining power to be to mirror that of cheap electricity?
Yeah.
Because that's the one thing one assumption about decentralization that we make.
Which is that if that cheap electricity is decentralized.
Yes.
Okay.
And so people like to say it's a waste of electricity, and they always say that without providing an alternative, something else that is decentralized, plausibly, and can be proven simultaneously.
Mm-hmm.
Power is the only thing that fits that bill. Conceivably, time is decentralized. Conceivably, space is decentralized, but I just don't see how you can prove consumption of those resources.
Mm-hmm.
Right. And the problem with proving the correctness of the previous block is that it takes us a while. And so whoever has the fastest hardware will be able to finish that step and start the lottery in the proof of work step sooner. And they will have a consistent advantage. And so I propose some mechanisms to work around that issue. And then in regards to the time-locked mining reward, that's difficult because
But
of.
hang on. Let's
Go ahead.
dwell on the first one for a second. So the mechanism would be that there's a proof of work step analogous to Bitcoin, but then there's a follow-up step which also takes up time, which is a lottery mechanism that decides who gets to add the next block to the chain.
No. The lottery mechanism is the proof of work step, as in Bitcoin, and that's the second step, not the first. The first step is producing the proof of correctness of the previous block,
Ah, okay.
and so after you're done producing the proof of correctness of the previous block, then you can start the lottery mechanism, which is essentially you guess a nonce, you hash the block, and you win if the hash of the block is smaller than the target difficulty.
Okay.
All right, and then in regards to the the split mining reward, it's difficult because in the context of mining pools, at least, you have multiple people contributing to
But
a block.
hang on. Explain again what that is. The second one.
The split mining reward
Yeah.
is where the protocol says the mining reward is split into two parts. 50% is liquid immediately. You can spend it the second
Right.
you've mined the block. The remainder is locked up for 4 years.
But maybe we can zoom out again 1 second, because what characteristics are you looking for in a reward mechanism? Because why is the first one not good enough? Like, why do you even have to consider a second?
First one being what now?
The first mechanism that you described, the one with the two-step.
A naive implementation of that mechanism gives the faster hardware a systematic advantage over slower hardware. And it skews the distribution of mining power in favor of fast hardware and out of favor towards cheap power.
Okay. And the second one ameliorates that.
The second one being the split mining reward.
Yeah.
It has no effect whatsoever on that calculus. It's another reason why the distribution of mining rewards is difficult. The solution to that calculus is for the prover to leave a portion of the mining reward unclaimed, which will then be claimed by whoever wins the lottery in the second step, where you hash and win, guess nonce and hash, and then you win if the hash of the block is smaller than the target.
Okay. And there was a third one?
And the third reason why the distribution of mining rewards is difficult, hang on, I have to check my notes, is dynamic block intervals. And so the idea is, if the network is capable of supporting a faster block interval, then it would be a shame not to have it. The question, if you want to get faster finality, right? If you want to reduce the block time from 10 minutes to 5 minutes, or from 5 minutes to 1 minute, the question is always, what are you sacrificing? And typically what you're sacrificing is a higher probability of a block race. So yes, your transaction is confirmed, but you're not actually sure that this confirmation has the same strength that it would have on Bitcoin. And so there is an indicator when the network has sufficient connectivity that lowering the target block interval will not significantly change the probability of a block race. And this indicator is the orphan rate. It's an approximation of the number of orphan blocks per actual blocks. And so you could say, if the orphan block rate is below a certain threshold, then we can afford to reduce the target block interval.
Okay.
And you would be reducing the target block interval without simultaneously increasing the probability of block race.
Right. Okay. So these three are not three different mechanisms, but they're three different considerations.
Three different considerations addressing three different considerations tied to the topic: how does the miner reward distribution happen?
Okay. And is there a conclusion?
There is. Let's see. Let me scroll down.
I think you should do a dedicated video on the article where you go into more depth. That's an aside.
Okay. I'll bear that in mind. Um, yeah, the conclusion is little more than a summary and a call to action.
And so how, because when you go to mainnet launch, you need to have some mechanism in place. Um, how does what you plan to have in place relate to what's discussed in the article?
Right. Um, so the plans are kind of up in the air. Like I said earlier, we're thinking of um, reducing. Excuse me. We're thinking of maybe launching without succinctness, and in this case, hang on. Let me turn on the electricity here before my laptop runs out. Here we go. Yeah, so we're thinking of launching without succinctness and then building in succinctness at a later hard fork. And if we go down that route, we would have to think about which other features we want to drop out of engineering considerations. The partially time locked mining reward, that one is already there. Well, it's there for the pre-mine. So the pre-mine, as you know, is locked for 6 months. That means that the logic for time locking mining rewards is there. Um, so I think we're unlikely to drop that one. The um, dynamic target block intervals, I think we're probably going to postpone that. Because it's just some research that we need to do, and that maybe we don't have time for. Also, implementation wise, it would be difficult, and it's doubly difficult to implement this, as the article explains, if you are targeting a succinct blockchain where you prove the correctness of the previous block. The reason why it's difficult to implement this is because you need the network to be aware of the orphan rate, and you only get to see the previous block because it's a succinct blockchain. So how do you know what the number of orphans was in the last 100 blocks, in the last 1,000 blocks? Well, you could keep a counter, but then how do you know how much to subtract from the counter as the window moves? Um, so there's I came up with some process control logic to follow that, but I mean, process control logic is not my forte, and this stuff needs to be analyzed from a security point of view. Um, yeah, does that answer the question?
Yeah, more or less. So you've got a solution. There's going to be.
Oh, I should mention that testnet right now has an adequate fixed um, difficulty adjustment mechanism. What is it? The thing that is fixed is the target block interval,
Mhm.
and so we could run with that. Um, and then another question is whether we integrate awareness of orphan blocks even without making the block interval dynamic. It's a worthwhile tool to have in defending against selfish mining attacks.
Mhm.
So the space of scopes that we could have for the block logic is rather large. Um, I mean, the scopes that we could have prior to launch with the intention to add the remaining features at a later point.
Okay. Cool. Very technical episode. Um, but yeah, useful update nonetheless.
Great. Talk to you
think
next week.
yeah, I think we can call it quits there. Good luck
Sounds
next
good.
week, and then
Thanks.
we speak then.
Exactly. Take care.
Ciao.